Let me welcome our last speaker for this session, who is Dr. Robert Warmbier from Wits University. And he's going to present a talk titled Elevating Material Simulations with Open Source from Consumer to Contributor. Welcome, floor is yours.
Thank you very much. I'm very happy to have a chance to present at this conference. I find it's an excellent networking opportunity, and I'm looking very much forward to make new contacts and get some faces connected to the names from all the nice colleagues from the CHPC who are helping me all the time. So that's a great opportunity for me. And because it's a nice networking opportunity, I want to first say something about myself, which I usually don't dwell too much. So I'm a computational physicist by training. Generally speaking, numerical methods applied to physics, yada, yada, yada. These days, working at Wits University, I'm basically doing material science 95% of the time. And I'm also the administrator of our teensy tiny local computational material science compute cluster. This just helps us a lot to get things done quickly when CHPC is overloaded. So that's really nice. So my research interests at the moment are basically electronic structure modeling in DFT. And for the theory/programming part, it's electron phonon coupling and Raman spectroscopy. I will be talking about that later. But I also am interested to some extent into the material science part, where I prefer energy materials, but I also work a lot with nanotubes and magnetic materials and so on. Whatever is interesting, whatever comes along, what the experimental colleagues throw at me. Okay, so we haven't had anyone talking about density functional theory yet today in this session. There was a nice workshop yesterday from the colleagues from England. So just a very, very short introduction what that is. So we basically take the Schrödinger equation, quantum mechanics, and we approximate the S out of the Hamiltonian so that we can do many particle physics. And then we are able to simulate in the order of a few hundred of atoms in a system, depending on what you want to do and what your resources are, obviously. And if I do very complicated things, I might go down to something with order of 10 atoms I can handle with reasonable resources. DFT scales relatively well on large computers. So depending on the software you're using, you can, in principle, scale up to a few thousand cores, where if I look at my colleagues overseas, if they want to play around over the weekend, they just take 1,000 cores and do whatever. So this is obviously not what we have resources for, but that is basically our benchmark, what we want to use. We have a fairly large memory footprint, so I'm talking here about RAM usages of hundreds of gigabytes, few terabytes for larger systems, and that's one of the reasons why we have very slow GPU adaptation in this field. Our GPU codes are usually still quite experimental, but also now you have like the current NVIDIA cards, they have maybe, 60, 80 gigs of RAM. So then you need like a lot of these cards, and then it becomes very expensive. At some point, it's not worthwhile going there. You just use more of the normal nodes, and you achieve the same with less money. And also, our simulations sometimes can take several days or maybe a few weeks, and that's then it's nice to have local resources because the CHPC queue is 3 days, and then everything always times out, and that's unfortunate. Okay, so there's a whole lot of software in this field, usually different software for molecular simulations and solid state physics because the basis sets are different. And like if you go back 10, 15 years, they were all very expensive closed source softwares like VASP or CASTEP or Gaussian, most of which are on CHPC available. Also, like just a side remark, that's why I put it in gray. These days, there are also a lot of graphical user interfaces, which make these kind of simulations more accessible. But I don't like them, and I never, okay, first of all, I don't have $10,000 to buy these. But on the other hand, I wouldn't give them to my students anyway, because what they enable you is to do simulations using techniques you don't understand. And because in DFT, you almost always get an answer, but you don't know whether it's a good answer. Research done with these kind of things without knowing what you're doing can be very fatal. So especially for students, I think it's best if they learn by hand first. Today, we also have a large ecosystem of open source software, and I'm a bit of an open source enthusiast. So I would always recommend using those instead. Okay, so this brings me a little bit to the purpose of my talk. So density functional theory is like many decades old, and if I just look arbitrary at the last 15 years, there are about 250,000 publications done using DFT. If I just chuck it into Scopus, 90,000 of which are from China. And we have a bit of 2,000 publications. That's not so bad. You know, it's competitive based on our size. And it's actually a method which you can see is used all over the country, not just for one or two universities, so that's really good. I think at UJ, we use primarily a DFT in chemistry. And University of Limpopo has the largest material science center, I believe, but it's spread all over the place. But then I was thinking, okay, are we actually contributing to the field? And I don't mean the specific fields you use the software for. Are we giving back to the community in terms of software development, in terms of theory development, right? So then I just looked at the top 300 rated cited papers on Scopus, and I found 2 with explicit mentioning of software development. Of course, many more might do software development hidden somewhere, but just based on the title, it was only obvious for 2, and that's a bit discouraging. And I also looked at a few reference articles. So usually if you have one of these big software packages, every now and then, 5 to 10 years, you write a reference article, and then everyone is supposed to cite it if you use the software. And Quantum Espresso in material science is the largest open source project. Not a single author or co-author from Africa. Up in it is the oldest open source project, well, one of the oldest open source projects in the field. Not a single author from Africa. My personal baby, GPaw, 1 author from Africa. That's me, and I don't think I'm necessarily counting because I'm not African. Well, I wrote the paper while I was here, so maybe that counts. Okay, but contributing is actually very easy, right? In a way, it's much easier than finding the resources for the simulations, right? Because you can access these codes freely, there's no boundary, and it is very good actually for us to contribute because it raises our visibility globally, right? If you look into material science, there are tens of thousands of researchers. It's very difficult for people to know you, right? But if you are an author on one of these reference papers, if you are the person in the chat who is responding to the answer to questions about a specific feature in the code because you wrote it, right? That raises your visibility, right? And that's good for us. So I think this is basically why I wanted to give this talk, is basically just this one point. So I could stop now. I'm hungry, sorry. Okay, but I have 10 more minutes, so I shall use them. Okay, as I said, my favorite project is GPaw, which is hosted on GitLab. GitLab much less evil than GitHub. It's coordinated primarily at the Technical University of Denmark, but it's not a fenced project in any way, right? You can just write a patch or write a new feature, you submit it to that web page, it gets reviewed, obviously, for quality control, and then if everything is fine, it lands up in the main repository, and everyone in the world can use it, and everyone in the world knows that you wrote it, right? So that's very straightforward. It's mostly written in Python, except for the really time-consuming stuff. So it means it's easy to use and easy to modify, right? Very quick, very easy. And we have a really awesome community on the matrix so that you can have very good discussions and feedback. Okay, so Python is really great for, I think, for scientific software, at least for the front end, right? Because if I look at the old codes, they're written in Fortran. I started my career with Fortran 77. Horrible input files, right? You just get the formatting slightly wrong, things don't work. Output files, text output files, horrible formatting, very difficult to parse, right? You have to make fancy, funny Perl scripts or whatever not, right? You don't have this in Python, right? You just write your input script. So this is basically a slightly longer than necessary code, which basically gives you an energy versus volume curve for cadmium telluride. And if I now had the time, I could in 2 minutes explain you exactly how it works, and you could reproduce it without a problem. Okay, and of course, from my point of view as a developer, which is even better, is in Python, I have direct access to the internals, right? If I take a Fortran code like Quantum Espresso and I say like, oh, I want to calculate a new observable, which is not currently in there, and I need the wave function to do that, I have to go in there. I have to figure out how internally the wave function is encoded. I have to then write a new piece of Fortran code, insert it there, recompile the code, which may not be easy if it's, for example, on the CHPC, right? And you have to compile your own version, and so on and so on. In Python, you just write your own routine in your own script, and it works. You don't have to touch the original code if you don't want to, so this is much less hassle. Okay, just a very, very quick example to illustrate minimum. So we use another software which is called Atomic Simulation Environment to give our atomic structure. And it, for example, has a database. It knows different things. So for example, it knows what a hydrogen molecule is. I can just get an atoms object in one line. I put it into a 5 by 5 by 5 angstrom box. Another line. I create a calculator object, in this case GPOR1 with a minimal input, one line. I run the simulation, and now that I have calculated this system, I can just go into the calculator object. It has as a in there a wave function object, and then I can now just get the wave function. I can just like one command, I get the pseudo wave function. In this case, also it has a method to just give me, for example, randomly chosen kinetic energy density. Okay, I can just with one line extract this property, and I can make a 2D cut, plot it, done. And to try to do just like getting this simple plot out of something like Quantum Espresso would take me several days. Well, I don't know several days, but it would take me a long time to extract this information neatly. Okay, so what do I want to say though is, I'm not doing this randomly, right? Why am I doing this? Why do I want you to do these kind of things? You need to find a need, right? Something which the current software just doesn't give you. And so, for example, I had a colleague at UJ, Professor Hearn. He's an experimentalist, and he said, oh, we're working on this metal organic framework, which has like 400 atoms. And it has a high spin phase and it has a low spin phase, and we want to know whether these two have different Raman signatures, because then we can experimentally test, if we do stuff with it, whether or not we can make the phase change. Okay, so I was like, oh dear, right? 400 atoms is a bit of a stretch for DFT. Okay, so I needed to do something, right? Okay, first I was reading up on Raman theory, which I will not now do, because of time constraints. Basically, I need to do it for solids. It's a bit more complicated than for molecules. I need two different ingredients. I need an optical transition. That's just dipole moment operator, bracket, blah, blah, blah. It's easy. And I need this nasty little bugger here, which is electron phonon coupling, which is naughty. Okay, electron-phonon coupling, what does it just mean is, usually when we do electronic structure, we assume that the atoms are not moving. And that, of course, is all not that true. Even at 0 temperature, the atoms would move. So there is a change of the electronic potential with respect to the movement of the atoms. And basically how this then interacts with the electronic states, that is our electron-phonon interaction. And we can use this not only for Raman spectra, but also, for example, to get quasi-particle lifetimes, which helps us, for example, to calculate conductivities. Right? If you just do normal DFT, you get conductivity. It's always divided by lifetime of the carrier, and that's not all that useful. Okay, downside is it takes forever. So this is just a very simple example for molybdenum disulfur. We get these beautiful peaks which almost look like the experiment. Okay, for my specific case, what was my need? I needed a Raman code. I needed to be spin aware because I had a high spin and low spin code. I needed to be fast because if I have 400 atoms, I need to do 3n calculations for 3n displays, and I needed to, 3n degrees of freedom, 2 calculations per degree of freedom, so a lot of calculations. And so it needed to be very fast, especially if I have this hole for 400 atoms. And my go-to used to be Quantum Espresso, but A, it's slow for this, and it's difficult to modify. It only had LDA Raman, yada, yada, yada. Up in it was just, yeah. The input files are just too horrible. So I went to GPOR, and it had some rudimentary facilities, some electron-phonon code in LCAO, which is very fast. And it was just very easy then to add the spin awareness to that myself. It took me a day, right? And then you run the simulation, and I get this little graph here that took a month to do on our homegrown system, where I then see, okay, I have different signatures for the two. This is a bit of a noisy thing because I didn't have the resources to do properly converged calculations. So this is a bit noisy, but basically the idea is that now the researchers, what they see is, for example, that if I change the temperature, I can see a peak wandering from here to here. And with that kind of thing, I can say like, oh yeah, I can confirm that this is the low spin phase and that is the high spin phase because I can identify these things. And what we then also wanted to show as a last step was, can we also do the same transition except with temperature with pressure? And basically, we can see, for example, that we have this line here shifted to the right, which is basically in agreement with our little simulation here. The rest is a bit funky. It's preliminary, right? So let's not look into all the nasty details. Okay, so I had my need, I had my will, and now what I just need is more students to do all the rest of the work. Okay, I have 2 minutes left, but I think that shall be enough for today. Thank you very much.